Now is it coming? Okay, good. So today I am going to discuss about two different techniques which were very approximate techniques of, I will not say field calculation, but field approximation. That means to give an approximate idea about the field distribution. Now, this actually is part of the evolution of this entire field computation or field determination methods. These are the initial methods that were developed. Now, in these methods, two methods, you cannot get the value of the electric field with very high accuracy. But what you can get is you can get a very clear idea about the distribution of the field, where the field intensity will be high, and if you want the capacitance of the system, you can get an estimate with about 5 to 10% accuracy. So at some point of time, not now, earlier, these methods were quite useful. Of course, later on, the numerical techniques have come, and nowadays we naturally go for numerical techniques. But what we are going to discuss in this particular today's class is, one is experimental field mapping and the other one is graphical field mapping. Now, what is experimental field mapping? Let us first look into it. Now, this method of experimental field mapping is actually based on the analogy of the stationary current field with the stationary electric field. So I repeat, there is an analogy between stationary current field with stationary electric field, which is given in table 2.1, that is this one, where this analogy is shown. That means in static electric field, we have the analogous quantity is electric current. In stationary electric field, we have the equation D is equal to epsilon into E. In electric stationary current field, it is J, that is the current density, is A, which is conductivity, into E. So now take in both these equations of static electric field and on the left hand side, we get, in this case it is flux density, which is like the analogous quantity is electric current, and therefore this is electric current density. And the material property which are analogous in these two cases are obvious from this equation of the previous row, that is dielectric constant, which means the permittivity, and volume conductivity. And then we know that charge can be, charge can be computed from the surface integral of d dot ds, where ds is the area vector, and in the same way the current can be obtained by the surface integral of j dot ds. So there is a very clear-cut analogy, and this is used in this experimental field mapping. Now here what is being stated is that if the medium between the two electrodes is isotropic, now you probably know what is called an isotropic medium. That means the material property is independent of the location within the region of interest. That means wherever you measure, the property will be same. Let me say it is a isotropic material, and not only that, this I mean, slight correction. What I said is that when the material property is same everywhere, irrespective of location, then it is called homogeneous material. Now, isotropic material means that anywhere you measure the three components of the material property. That means if you measure the material property along x direction, y direction, and z direction, they will be same. Then you call it isotropic. But in some material, this is not the case. As for example, I can give you the example of cold rolled steel, where the permeability of the material along the direction of rolling and in normal direction is completely different, and therefore cold rolled steel is not isotropic, it is an anisotropic material. Now, now the current density and the current density in stationary electric field and the electric field intensity and the electric flux density will be in the same direction. In other words, what I am trying to mean is that the current density and the electric field lines, they will be along the same direction. That comes from the analogy. So, for a given electrode system, if we take a slightly conducting material, this can be in the form of a conducting paper or an electrolyte, and this is placed instead of the dielectric material because we are using the analogy. So dielectric material is replaced by slightly conducting material. Now you can ask that why slightly conducting material. You can clearly see that a dielectric material, if it is an ideal material, there will be no current through the dielectric material. Then it should be completely non-conducting material. But we know that any dielectric material, the current through the dielectric material is never zero, so we put a conducting material which is slightly conducting so that this analogy remains same. Now, this is an important statement that if we travel along a line through an electric field and measure electric scalar potential as we are going or as we are moving, then the negative of the rate of change of V, because rate of change of V is nothing but the gradient of V, and negative of the gradient of V is definitely equal to the electric field intensity, and that is always in the direction of travel. So this equation 12.1 is quite well known. And if this del V del L minus del V del L is maximum, then it gives the value of E itself. Because by definition, the potential gradient is always the maximum value of that slope at a particular point, and that gives always the E. And there is an interesting observation. If the electric potential does not change with position, that means as we are moving and as we are measuring the potential, if the potential doesn't change, then the path of travel becomes equipotential and it will naturally be at right angles to the electric field. And this gives rise to the option that the electric field can be mapped by a voltmeter that will measure the potential difference and two probes, which can be as simple as two metal rods. and the two probes will be connected to the voltmeter, and then the two probes will be placed in various positions to measure the potential differences between the two probes. This has been explained or rather written very details here, so let us look at it, how it is done. If I want to determine the equipotential lines, so how do I do it? So what I do, I keep the probe at one point on that conducting paper and we put the probe there, fixed. And the other probe is moved. In whichever position the moving probe, because as the one probe is fixed, I am moving the other probe. So what will happen at one particular position of the moving probe, the voltmeter will record a zero reading. And the potential of the moving probe is therefore the same as that of the standstill probe. If we mark these two positions on the paper, naturally we can trace the equipotential. So you can see the beauty of the method. And then how do I trace the electric field lines? Well, that is also not very difficult. So what we do that the distance between the two probes we are keeping same, and one probe is again placed at a fixed point and the other probe is rotated. Why rotated? Because we are keeping the distance same between the two probes. And when we measure the equipotential, we can see it is very clearly stated that how I can map on that conductive paper the equipotentials and the electric field lines. And you can clearly understand that from these you cannot get the electric field intensity very accurately. However, by dividing the potential difference and the distance between the two points where we have measured, we can find the field intensity, but the accuracy will not be high. As I was telling, it might be of the order of maybe 10%, 5 to 10%. Now, why we use a slightly conducting paper? There is another reason which is also explained here. That in a real life voltmeter, let me tell you that if it is an ideal voltmeter, naturally no current flows through the voltmeter. But we all know that in a real life voltmeter, the voltmeter will draw some current. Now, if I take this medium as vacuum or air, then it will be very difficult because how do I supply the current of the voltmeter? So what we do, instead of putting simple air as a medium, we put that conducting medium, or rather slightly conducting medium, so that some current flows through that conducting medium, and that current itself will feed the voltmeter current, and therefore you will get a reading which is reliable. How do I get this conducting paper? Well, typically it is used paper impregnated with carbon. This is slightly conducting and it gives reasonably good results. There is an alternative where an electrolytic tank setup is used. That means we use a tank where we put a large sheet of laminated graph paper at the bottom of the tank. Then the tank is half filled with electrolyte, and the height of the electrolyte is kept same throughout the tray. And then we do in the same way, because now this electrolyte is acting as that slightly conducting medium, and in the equipotentials of the electric field lines are mapped on that laminated graph paper, which is placed at the base of the plate. Well, these are the methods. Let me tell you that even today, if we do it in a laboratory, it is quite interesting for the students. Although, if you ask me for a real life problem, you cannot use it. But as a method for understanding the basics of electric field, this is quite an interesting method. But then instead of all these experimental setup, then there is a second method which is called field mapping using curvilinear squares. Now, this basics is of course uh, on our all fundamental that statement that we have a conjugate harmonic function, that means which satisfies Laplace's equation, and these two conjugate harmonic functions are orthogonal to each other. And naturally, I have explained in my last class that these two are nothing but the equipotential and the electric field lines. And as I have explained in my last class on conformal mapping, this curvilinear square mapping also can be used only in two-dimensional fields. That means where the field is not varying along the third direction. Only in those cases it can be used. And again, just like the experimental mapping, this mapping is also good for visualization of the field distribution, but may not be so good if you want the exact results. Now, typically, what is a curvilinear square? Curvilinear square is, of course, a planar geometric figure, but it is not a true square because its sides are, its four sides are slightly curved and unequal. But as we reduce the dimensions of the curvilinear square, it will become a true square. This is what the concept of a curvilinear square. Now, the field map actually we get using this curvilinear square, as I have already said, gives a very good understanding and behavior of the field of electric field that we are going to study. And again, this theoretically, these are based on Cauchy-Riemann relations that I have already said that they are conjugate harmonic functions and etc. But I am not going into all that. What we are going to explain is what are the foundations of the field mapping. The construction of the field map is based on some significant features of electric field, as I have written below. What are those? Let us look at it. So, one, a conductor boundary is one of the equipotentials, which is quite acceptable. Number two, equipotential and electric field intensity, which is also same as, as far as direction is concerned, same as electric flux density. They are normal to each other. As a conductor boundary is equipotential, hence electric field intensity or electric flux density vectors will be perpendicular to the conductor boundaries, which is also basic field theory. And electric flux lines originate and terminate on charges. This is an interesting concept because we always say that the flux lines, they originate at the positive charge and terminate on the negative charge. Hence, if we consider a homogeneous medium and charge free, that means within the dielectric there is no charge, we can say that the charges will be always on the electrodes, and therefore we can say that the electric flux lines will originate from one electrode and will terminate on the other electrode. So these three foundations, I mean, based on these three foundations, we've actually go for the field mapping. Now let me explain it with the help of this diagram, which is a two-dimensional field, a concentric cylindrical system. The inner cylinder is live, it has a potential of V, capital V. The outer cylinder is R, it has a potential of 0. What I am now saying is that let us consider one particular field line or flux line originating from the point X. Here you can see point X on the live electrode. And as I have said that I am considering an homogeneous dielectric as well as charge-free dielectric. So the field line will originate from one electrode and terminate on the other electrode. So this field line originates from X and terminate at X prime. If I take another field line which originates at Y, then it will terminate at, let's say, Y prime. Fine, that up to that point it is fine. But then there is an interesting concept that since field lines are like this, then if you take any other field line between X and Y, it will originate from live electrode and terminate on the earth electrode, and it cannot cross another field line because then the basic concept of that orthogonality will be violated. Or in other words, we can say that all the flux lines that will be originated between X and Y will be terminated on the earth electrode between X prime and Y prime. So therefore, what is happening that X prime and Y prime is acting like a flux tube. That means all the fluxes entering this tube at XY, they will not cross the boundary, they will terminate on X prime, Y prime. This is a very interesting concept. Maybe somewhere you will hear it in your life, the concept of flux tube. Don't get confused. This is as simple as that. That if you take two field lines and then all the other field lines within these two field lines cannot cross the other these two field lines that you have considered, and therefore all the flux within that will act as, I mean, will be like a flux tube. So therefore, I can define another flux tube which will originate between Y and Z and terminate between Y prime and Z prime and so on and so forth. That's fine. Now, what we are going to do is how I am going to sketch the curvilinear square. So now what I am saying that considering the length of the line joining the points X and Y, let's say del S. What is this? Look at this figure. The line which I am joining X and Y on the live electrode, this is del S. The flux in the tube XY, let's say del psi. That means between X and Y, the total flux that is being originating, let's say it is del psi. Then what is the flux density? That will be del psi divided by del S into 1. Now why 1? Because we are considering two-dimensional system. Therefore, we are considering unit length perpendicular to your display. So the area perpendicular to this flux del psi is del S, which is length of the line between X and Y multiplied by the unit length perpendicular to the display. So that is written as equation 12.2, that flux density will be del psi by del S with respect to this diagram. Fine. Now let us consider it in another way, that we consider that the permittivity be epsilon and electric field intensity at the midpoint of the line, therefore, will be given from equation 12.2. Why midpoint? Because this is like a mean value theorem, that if the variation is uniform, we can always take the mean value at the midpoint. So this E is 1 by epsilon del psi by del S, that is 12.3. Alternately, there is another way of determining the field intensity. How? That's how we are now going. That let's say the potential difference between the point x and x1. And what is x1? It is another equipotential. Then let's say this potential difference is del phi between x and x1. And let's say that the distance between x and x1 is del L. Then you know that del phi by del L will be electric field intensity. So that is here equation 12.4. And now if I consider del S and del L to be small, then I can say they are equal and I write equation 12.5. That means equation 12.3 is equation 12 is equal to equation 12.4, and then we write that del L by del S is equal to epsilon into del phi by del psi. For sketching the field map, we are considering homogeneous dielectric having a constant permittivity, constant amount of electric flux per tube, that is del psi we are keeping constant, which is, I mean, it is like that we are taking these lengths between x and y same along the entire live electrode, then I can safely assume that this flux will be same. So we are assuming that constant amount of electric flux per tube and constant potential difference between the two consecutive equipotentials. So this is another, I mean, we are trying to map it in this way that this, uh, what is being stated here again, you read constant potential difference between two consecutive equipotentials. That means here you can see phi is equal to V is the electrode, then one equipotential, one circle, another equipotential, another circle, and the potential difference between two consecutive equipotentials, we are saying that we are keeping that same. If I do say that, then if this del phi and del psi, if they are constants, epsilon is also constant. So what happens is I can say that this del L by del S remains constant. Or in other words, the ratio of the distance between field lines as measured along an equipotential and the distance between equipotentials as measured along a field line must be maintained constant and not the individual length. This is the important point. That means we are not keeping del L and del L equal to constant or del S equal to constant. What we are keeping is this ratio constant. That means if I go back to the figure, what is del L? Del L is the distance between two equipotentials, that is x and x1. What is del S? It is the distance between x and y. So we are keeping only this ratio constant. We are not keeping the individual lengths del L and del S constant. Now this constant is an important quantity. So you can always ask that what should be this constant. And the most commonly we take this constant as unity. That means we take del L is equal to del S. So that's what here is written here. And if we do that, then this field map that we are generating is actually curvilinear squares. So uh, what is important here is written another point here. Just see the product of electric charge and electric potential difference is the energy of the electric field. It is very well known. And we also know that electric charge and electric flux has a one-to-one correspondence, particularly in the SI unit system. That means We know that 1 coulomb of charge produces 1 coulomb of electric flux. Therefore, if we have a field map and if del psi and del phi they are kept constant, therefore their product will remain constant and therefore energy of the electric field remains constant. So what does it mean? Therefore the curvilinear squares having the same ratio as given by equation 12.5, that means del L by del S, that ratio, they will always have the same energy stored in electric field regardless of the size of the electrode. That means if you keep this del L by del S constant, and as you move from the electrode, live electrode to earth electrode, naturally your del L and del S will keep on increasing. But if you keep this ratio constant, then in each curvilinear square the energy will remain the same. So construction of the curvilinear square field maps. So what is being done? The field lines and the equipotentials are typically drawn on the original sketch, which shows the conductor boundaries. That means the sketching is started with the conductor boundaries. Then arbitrarily one field line is begun from a point on the surface of the more positive conductor with a suitable value of del L, and in equipotential is drawn perpendicular to the field line with a value del S by del L, which is something like this. I repeat that I take the point AX and then I move perpendicular to the conductor, take a small uh, length del L, and I identify the point X1. Then what I do, I take a small length del S and I identify the point Y, and again I move perpendicular to the conductor and I identify Y1, and then I join X1 and I1, and that becomes my first equipotential. Then what I do, I take from Y to Z another point and keep del S constant, and then move perpendicular to the conductor and I identify the point Z1 and I join Z1. In this way, and the entire first equipotential is drawn. Then I take the point X1, which is on the first equipotential, and I move along this, perpendicular to the equipotential, and I take this distance between x1 and y1. Now it becomes my del S, and this del L by del S, this ratio must remain constant. So whatever ratio is del L by del X, that is the distance between X and X1 and X and Y, this ratio I know already. So I have calculated, now I can calculate the distance between X1 and Y1. Then this ratio remaining same, I find out what should be del L. So I find the point X2. Similarly, from Y1, I move perpendicular to the equipotential, I find the point Y2. Then from Z1, I move along perpendicular to the equipotential, I find Z2, and I draw the second equipotential. In this way, I gradually move towards the earth electrode and keep on drawing the equipotentials and, of course, the field line. So when I have drawn enough number of equipotentials, you will see that you have prepared the field map. This is a very interesting way of preparing the field map. You can try it with a graph paper at your home. This is very, very nice way of drawing a field. In fact, I have done when I was a student, because that time there was a computer, so we did it on the field map, and it was really, really, I must say it was very, very exciting. But as one thing I have to say that construction of a satisfactory field map using curvilinear squares is a trial and error process. There is no hard and fast rule, and it involves continuous adjustment as and refinement. So the field map is fine-tuned through successive subdivisions to form a dense field map. That means initially we draw a field map which have relatively larger distances of del L and del S, and then we can subdivide to form a denser field maps. So this is only one thing which you will be able to understand if you do it yourself, that how beautifully this can be done. But then one question that we have to answer is, I earlier told that we can estimate the capacitance from the field map. The how? That's of course I have to answer. Well, let us look at this, that we all know that capacitance is Q by V, where Q is the charge on the conductor and V is the potential difference. Now, applying Gauss's law on a Gaussian surface enclosing the conductor having more positive potential, Q will be naturally equal to psi, where psi is the flux coming out of the conductor, because there is an 1:1 relationship between charge and the flux. So we can say that capacitance can be calculated by flux divided by the potential difference. Now, if I take an isolated curvilinear triangle, it is something like this, that on the equipotential, the flux is del psi, the distance is del s. Along the field line, the potential difference is del phi, the distance is del l. So what do you do? To calculate the capacitance with the help of curvilinear rectangle, when we are saying rectangle, this del L is not equal to del S, because I said this ratio has to be maintained constant. If I make this ratio 1, it becomes curvilinear square. If you take any other value, it will become curvilinear rectangle. So let the flux through this be del psi and the potential difference is del phi. Then we can always say that the flux density may be assumed uniform, so that this E into del S into 1 that I was telling multiplied by epsilon, that will be equal to the flux density, because epsilon into D is the flux density. Then electric field intensity and electric potential difference, we know that del phi will be E into del L. So therefore, if we substitute, I get this del psi is epsilon into del S del phi by del L. So therefore, from here, if you take del psi by del phi, that becomes del C, that is a small capacitance. What is that? It is the capacitance of the small curvilinear rectangle. That is del psi by del phi, that is here. Del psi by del phi will be the capacitance of this curvilinear rectangle. And how much it is? It is given by permittivity epsilon into del S by del L. That means just from this two ratios of the lengths, I can get a clear idea about the incremental capacitance of one small curvilinear rectangle, and the total amount of flux emanating from one conductor and terminating on the another conductor. How can I get? Well, it comes back to like here again. See, this is the conductor, and we are saying that between 2 points x and y, the flux is del psi. And in this way, if there are infinite number of such small elements, then the total flux is del psi into n psi. So that's what is written here. Here, the total number of flux is, I just sum up the del psi of one particular curvilinear rectangle and then just add up how many such curvilinear rectangles completes this entire, the equipotential. Then how do I find the potential difference? Again, let me go back to this. Yeah, here. Now if you take the line x and x prime, the potential difference is V. But now I can do it in this way that the potential difference x and x1 is del phi. So if I keep on adding all these potential difference for how many rectangles, let's say I have infinite number of rectangles in the radial direction, that means in the field line direction. So there are inside number of such rectangles in the along the equipotential direction, and there are infinite number of rectangles along the field line direction. So if I add the potential difference for the infinite number of rectangles, I get the potential difference V. So that's what it is written here. So V is nothing but N phi into del phi. Of course, we assume that del phi is same between two consecutive equipotentials. So therefore, capacitance per unit length between the two conductors, then how it will be given? C will be given by psi by V, where psi is n psi into del psi, V is n phi into del phi, where del psi is the flux in each flux tube, and then n psi is the number of such rectangles forming how many flux tubes along the equipotential direction. Then del phi is the potential difference between two equipotentials, and n phi is how many such rectangles are there along the fill lines. And then if you put this expression for del psi by del phi, then and substitute this representation in terms of del s by del l, and you can see that del s by del l, if I take this equal to 1 or whatever this constant, then it becomes that it is this capacitance is nothing but epsilon multiplied by a constant, which is the ratio of del s by del l, and n psi by n phi. So therefore, what I can get is that I can clearly get the idea about the capacitance by simply counting the number of these curvilinear rectangles multiplied by this epsilon, which should be known, and multiplied by this ratio of del L by del S, and that ratio must be known, otherwise you cannot draw the field map. So how do I find the capacitance? Again, I come back. So it is a very simple statement that you take these flux tubes and count how many are there. Of course, it depends on your field map. If you have a denser field map, you will have more flux tubes. If you have a little bit of coarse field map, you have less flux tube. But you count the flux tubes, how many along the equipotential. Then you move along the field lines and count how many rectangles are there. So in this way, you calculate n psi along the equipotential and n phi along the field line. Take the simple ratio of n phi and n psi, which are two numbers, and obtain from the field map, and you get C. Now that's quite a brilliant way of representing the capacitance of the system without going into any sort of computation. Yes, it may not be very accurate, as I said, but you can. A good field map, once done, gives 5% accuracy, which in many cases people accept in our life, the real life. So you can see that what I have explained today are two methods. One, experimental field mapping. The second is graphical field mapping. And in both these two cases, I won't say that this will be used for practical applications today, but it is, it is very good for understanding the field. And if you have some time, take one graph paper and try to do this graphical field map. It will be so good. Or alternately, if you are good in software, just write a code to develop the field map for, that is it, yeah, this one. Just develop the code for writing for creating the field map for this concentric cylindrical system. You will be, really getting an insight of the field. So, I mean, this is just like, if you are really interested and if you can do the coding, you will see that You can do it. I can tell you that earlier I have seen students have done it. So if you are interested, you can do it. Well, students, so that actually is the final class of your course that I am taking this semester. So all the best to you, and you have all the notes. So this particular note you will get today. So study all the notes. I generally go to the university as I mean, whenever I have time. I mean, during the lunchtime or not. So if you are interested, you can come to the university and meet me. And particularly, I feel that it is very important that I know my student. Just for example, I find only one small rectangle on my screen with whatever photograph you have put. I don't know anybody is listening, or I mean, I have no idea. So actually, it is always better that I know my student. And without knowing my student, one thing I tell you very clearly that see, I get requests later on that give me recommendation letter. But if I don't know my students, I will not give recommendation letter. So, I mean, this is something I follow very strictly that if I don't know a student, I don't give recommendation.